Hello, everyone, and welcome. Today, we are going to unpack the data science context, exploring why this field has become an absolute necessity in the modern world, how raw inputs transform into strategic power, and the precise life cycle a data scientist follow to solve real world problems. Whether you are completely new to the topic or looking to consolidate your foundational understanding, this session is designed to map out the entire ecosystem clearly. Now, to kick things off, let's start with the absolute building block of this entire discipline, the concept of data itself. When we look at the core of our field, we must ask what is data? In its purest form, data is simply the lowest level of abstraction. It represents raw representations of facts, figures, text, observations, or ideas. On its own, raw data actually carries zero meaning. Think of it like scattered zigzag pieces on a table. It only transforms into valuable information when it is systematically structured, given context, and interpreted by humans or algorithms. Today, data surrounds us in countless forms. It's the number in our financial spreadsheets, the text in our messages, the pixels in images, video clips, and audio files. Now, coming to types of data. Some of the common types of data include text, image, video, numbers, spreadsheets, and sound. But as engineers and analysts, we can't just look at data as an unorganized pile of files. We have to classify it mathematically. Let's look at how statistics breaks data down into two primary pillars. In statistics, data is cleanly divided into qualitative data and quantitative data. Coming to qualitative data, it is a categorical and descriptive data. It captures attributes that cannot be measured with math, such as person's eye color, a product brand, or a custom text review. Quantitative data, on the other hand, is entirely numerical. It represents quantities that we can run calculations, sums, and averages on. If we pull back the layers even further, these two categories split into four foundational subtypes that dictate exactly how algorithms treat them. Let's look at those next. First, under qualitative data, we have nominal and ordinal data. Nominal data consists of names, labels, or categories that have absolutely no inherent order or hierarchy. Examples include gender, country of birth, or a smartphone brand. One isn't mathematically greater than another, they are just different. When it comes to ordinal data, introduces a clear sequence, scale, or ranking. Think of customer satisfaction ratings from poor to excellent or academic grades from A to F. The order matters immensely, but the mathematical distance between the points isn't perfectly quantifiable. Second, under quantitative numerical data, we have discrete and continuous data. Coming to discrete data, it consists of distinct countable values with fixed gaps. You can think of this as integer counts. For example, the number of employees in a company or the number of cars in a parking lot. You can have 14 or 15 cars, but you can never have 14.3 cars. Continuous data represents information that can be split into infinite fractions along a smooth spectrum. Things like temperature, precise, height, weight, or time elapsed. It can be measured down to as many decimal points as your instruments allow. Now, let us see what is data and evolution of data. These slides give us a visual consolidation of what data is and how our understanding and volume of data has evolved over time. The evolution of data is truly staggering, from handwritten records to digital databases to cloud based data lakes storing petabytes of information. We now live in what is called the data age. Every click you make on the internet, every transaction you process, every photo you upload, it all generates data, and the pace at which data is being created is only accelerating. So, where does all this data come from? This slide covers the concept of data sources. Data sources are the origins from which data is collected. These include social media platforms, IoT sensors, business transactions, government databases, scientific instruments, customer interactions, and many more. Understanding data sources is crucial because the quality, reliability, and type of data you get depends heavily on where you collected it from. Data from a controlled clinical trial is very different from data scrapped from Twitter. Now, here is a question that many students and even professionals confuse. Are big data and big science the same thing? The answer is no, they are not the same thing. Let me use a beautiful analogy from this slide. Think of big data as a crude oil. Big data is about extracting that crude oil from the ground, transporting it in mega tankers, siphoning it through pipelines, and storing it in massive silos. Data science, on the other hand, is about refining that crude oil, turning into fuel, plastics, medicines, essentially making it useful. So, big data is the raw resource, data science is the refinery that adds value. You need both, but they are distinct disciplines. So, what is data science? Alright, so we now arrive at the heart of our module. What is exactly data science? Data science is the study of data to extract meaningful insights for business. It is a multidisciplinary approach, meaning it borrows from multiple fields. It combines principles and practices from mathematics, statistics, artificial intelligence, machine learning, and computer engineering to analyze large amounts of data. And the kind of questions it helps answer are powerful ones. What happened? Why did it happen? What will happen next? And what can we do about it? This four-dimensional questioning framework is what makes data science so incredibly powerful for business and governments alike. So, why has data science become so critical? Let me walk you through this. Modern organizations are absolutely inundated with data. We have a proliferation of devices that automatically collect data and store information. Smartphones, smartwatches, smart sensors in factories, online systems, and payment portals capture enormous amounts of data in e commerce, medicine, finance, and virtually every aspect of human life. We now have text, audio, video, and image data available in vast quantities. And without data, all of this data would just be noise. Data science gives organizations the ability to convert this noise into signal, into actionable insights that drive real decisions. Now, coming to data science visual and career landscape. These slides highlight the visual representation of data science ecosystem and also reference something very exciting, the career and salary prospects in data science. Now, let's see the differences between these core roles so no there's never any confusion. In the tech industry, we often see three titles used interchangeably, but they are fundamentally different: data analyst, data scientist, and data engineers. Let's break down these unique responsibilities of these three categories. First, when it comes to data analyst, he primarily looks backward and at the present. Their core job is to ask what happened and what is currently happening. They take structured data sets, run SQL queries, clean minor errors, and build beautiful interactive dashboards in tools like Tableau or Power BI to keep business leaders informed. And the second one is data scientist. He looks forward. Their core job is to ask what will happen and how can we optimize for it. They run advanced experiments, manage messy unstructured data, and write code in Python or R to build predictive machine learning models that uncover hidden future plans. And at final, the data engineer. He is the master architect. They don't typically build the final models or business charts. Instead, they build and maintain the heavy infrastructure and data pipelines that make everything else possible. They utilize tools like Hadoop, Spark, and cloud architectures to move massive volumes of data safely from point A to point B. Now, let's look at some concrete real world applications of data science. And I want you to think about these because you probably interact with some of them every single day. Firstly, predicting interest of the audience on different online video streaming platforms. Think Netflix, YouTube, Hotstar. When Netflix recommends you a show to you, that's a data science model at work, analyzing your viewing history, genre preferences, and even the time of the day you watch. Secondly, getting insights from customer reviews in online stores and food delivery apps. When you order on Swiggy or Zomato and the app says most popular dish at this restaurant is paneer tikka, that insight comes from data science. Thirdly, effective targeting of advertisements. Ever notice that after your search for shoes online, you suddenly see shoe ads everywhere? That's data science powering targeted advertising. Data science is literally everywhere around us. Now, what is data science? This slide reinforces our definition beautifully. Extracting meaningful insights from data is known as data science, and when data is investigated and carefully analyzed, it provides insights which enrich our data lives. I love this framing because data science isn't just a technical discipline for businesses, its insights enrich lives from predicting disease outbreaks to optimizing crop yields to improve traffic systems. Data science makes the world better. Now, coming to applications of data science, the domains. Let's look at the broad domains where data science is applied. Defense and security, analyzing threat intelligence, predicting cyber attacks, natural sciences, climate modeling, geno- genomic research. Engineering, predictive maintenance of machines, quality control, and when it comes to finance, fraud detection, risk modeling, algorithmic trading, and when it comes to insurance, pricing risk, detecting fraudulent claims, political policy, voter behavior analysis, policy impact prediction. The breadth of these applications should tell you something important. A data scientist is not limited to one industry. Your skills are transferable across sectors, which is one of the most valuable aspects of choosing this field. Now, let's talk about how data science actually helps answer different types of questions. This is really exciting because it shows you how intellectual diversity of what data scientists do. There are four categories of questions. Now, let's see some common questions to ask from data are: which class does this belong to, A or B? Is this an outlier? What will probably be the value of this variable? What should be done now? Now, let's analyze these four category questions. First, which class does this belong to, A or B? The answers to these questions come from a definite number of options. Will it rain today? Yes or no. Will the weather come from a definite number of options? Will the weather be hot or cold? Hot or cold? To answer these, we use a family of algorithms called classification algorithms. They look at patterns in historical data and classify new data points into categories. Secondly, is this an outlier? Sometimes the goal isn't to classify, but to find anomalies, things that don't belong. Is this email spam? Is this bank transaction fraudulent? Is my tire pressure reading normal? The algorithms that answer these are called anomaly detection algorithms. Third one, what will probably be the value of this variable? Here we predict numerical values. How much rainfall will we receive this year? 100 mm? How many runs will the winning team score? 320? For these, we use regression algorithms which model relationship between variables. Fourth, what should be done now? This is the most advanced category. used in autonomous robots and self driving cars. Based on the environment, what action should the system take? This is solved using reinforcement learning, a branch of machine learning where an agent learns by trial and error to maximize rewards. Now, let's formally address the need for data science. Why data science? This is crucial because before you adopt any technology, you need to understand why it is needed. Data science has become an essential field to the growing importance of data in decision making, innovation, and automation. Key drivers include the explosion of data. Massive growth in data from digital sources demands advanced analysis techniques. We are generating more data in a day now than in all of human history before 2000s. Hidden patterns and insights. It is meaningless. The raw data in this looks meaningless. Data science helps extract meaningful patterns and knowledge that humans simply cannot see manually. Data driven decision making. In this, organizations can now make informed, evidence based decisions rather than relying on gut feeling or guesswork. Competitive advantage. Business that effectively use data science gain an edge through insights, automation, and personalization. Automation and AI. Data science powers intelligent systems and automates complex tasks using data models. And at last, societal applications. It solves real world problems in health, agriculture, governance, and more. Now, knowing all this, let's ground everything with a real project example. Because theory without practice is incomplete. Let me share a wonderful analogy for what a data science project looks like. Here's my favorite analogy for a data science project. Think of it like cooking. First, you collect ingredients, that's your data. Then you can clean and prepare them, that's data cleaning. You explore that taste combination work, that's exploratory data analysis or EDA. Then you cook, that's model building. You taste and refine, that's evaluation and tuning. And finally, you serve, that's deployment. This cooking analogy becomes beautifully capturing the end to end pipeline of a data science project. Keep this in mind as we go through the formal workflow. Now, let's make this more concrete with a real example project. The goal is to build a model that predicts how many bicycles will be rented tomorrow based on weather and past usage data. The outputs of this project would be a visualization, a graph showing how rental demand increases as temperature rises, a model for example, a random forest model that gives the best accuracy, a dashboard that explains something like expected rentals tomorrow. 358 bikes. This is a realistic practical data science project and it nicely illustrates how data science adds business value. A bicycle rental company can use this plan their inventory, staff scheduling, and maintenance better. Now, let's go through the formal data science workflow, which has 10 important steps. And I'll explain each one using this bicycle rental project as the example. Coming to step 1, problem definition. Understand what we want to solve. In our case, predict the number of bike rentals to help a rental company plan inventory. Step 2, data collection. Gather data from data sources. Here, what we get historical bike rental data plus weather information like temperature, humidity, and wind speed. Step 3, data cleaning. Fix errors and missing values. For instance, handle missing temperature values. Remove duplicate entries. Correct wrong timestamps. Step 4, exploratory data analysis or EDA. Analyze patterns and trends. Check if weather affects rental count. Create graphs showing demand versus temperature. Step 5, feature engineering. Create new useful variables like season. Is it a weekend or weekday? Is it a holiday? Feels like temperature. These are engineered features. Step 6, Model selection. Choose suitable machine learning algorithms. We might try linear regression, random forest regressor, or XGBoost. Step 7, Training and testing. Train the model on past data and test its performance. We'd split data 80% for training and 20% for testing. Step 8, Model evaluation. Measure how accurate the model is. We use metrics like MAE, mean absolute error, RMSE, root mean square error, and R squared score. Step 9, Deployment. Deploy the model so users can access it. Create a web or app dashboard to show tomorrow's rental prediction. And step 10, final step, monitoring and maintenance. Update and improve the model over time. Every month, retrain the model with fresh rental data. This 10-step workflow is the backbone of virtually every data science project in the industry. Now, coming to project outcome. After going through this project, you would have understood the pipeline end to end from problem definition to deployment. Learn where each tool fits. For example, Pandas for data cleaning, Scikit-learn for modeling, Power BI or Tableau for visualization, and most importantly, you have learned to solve real world business problems using data. This is exactly the kind of mindset we want to cultivate, not just theoretical knowledge, but applied problem solving thinking. Now, let's formally look at how data science is used. There are four types of analysis in data science: descriptive analysis, diagnostic analysis, predictive analysis, and prescriptive analysis. Number 1, descriptive analysis. This answers what happened. Think of monthly sales reports. You are describing past events. Number 2, diagnostic analysis. This answers why did it happen. For example, if sales dropped last quarter, diagnostic analysis investigates the reasons. Maybe a competitor launched a product or there was a supply chain issue. Number 3, predictive analysis. This answers what will happen. For example, forecasting future sales based on trends. This is where machine learning models really shine. Number 4, prescriptive analysis. This answers what should we do. This is the most advanced form. It doesn't just tell you what will happen, but recommends specific actions to improve outcomes. These four types form a progression from hindsight to insight to foresight to action. And mastering all four is what makes a complete data scientist. And these are the elaborated parts of the different types of analysis. Descriptive analysis. Descriptive analysis examines data to gain insights into what happened or what is happening in the data environment. Coming to diagnostic analysis. Diagnostic analysis is a deep dive or detailed data examination to understand why something happened. Coming to predictive analysis. Predictive analysis uses historical data to make accurate forecasts about data patterns that may occur in the future. Lastly, prescriptive analysis. Prescriptive analysis takes predictive data to next level. And this is the graph between value and complexity using different types of data analytics. These are the some of benefits and uses of data science: making better business decisions, making the measure of performance, providing information to internal finances, developing better products, increasing efficiency, mitigating risk and fraud, predicting outcomes and trends, improving customer experiences. Now, coming to application areas of data science. These slides give you a rich visual landscape of all application areas of data science across multiple sectors and industries, from healthcare to agriculture, from sports analytics to smart cities. The reach of data science is truly global and profound. Each of these domains has unique challenges and unique data sets. And as a data scientist, your ability to adapt your skills to a new domain is just as important as your technical knowledge. Coming to data science process flowchart. Now let's shift gears and talk about the data science process in more formal detail. We are going to follow the O'Neill and Scott framework, one of the most respected process models in the field. This flowchart gives you a bird's eye view of complete data science lifecycle. Let's walk through the each step carefully. Step 1, define the problem and create a project charter. Clearly defining the research goals is the very first step. The project charter outlines the objectives, resources, deliverables, and timeline, ensuring that all stakeholders are aligned before any work begins. This is critical because if you don't know exactly what problem you are solving, no amount of data or algorithms will help you. Coming to step 2, retrieve data. Data can be stored in databases, data warehouses, or data lakes within an organization. Accessing this data often involves navigating company policies and requesting permissions. This step is often underestimated. In practice, getting access to the right data can be one of the most time consuming parts of any project. Step 3, data cleansing, integration, and transformation. Data cleaning ensures that errors, inconsistencies, and outliers are removed. Data integration combines datasets from different sources, and data transformation prepares the data for modeling by reshaping variables or creating new features. This is often called data wrangling, and it typically takes up to 60 to 80% of data scientists' time. Coming to step 4, exploratory data analysis or EDA. During EDA, we use various graphical techniques, scatter plots, histograms, box plots to visualize data and identify trends. This phase is like getting to know your data. It helps us to select the right modeling techniques. EDA is where a lot of creative and initiative work happens in data science. Coming to step 5, build models. In this step, machine learning or deep learning models are built to make predictions or classifications. The choice of algorithm depends on the complexity of the problem and the type of data. We might try multiple models and compare their performance. Step 6, present findings and deploy models. Once the analysis is complete, results are present to stakeholders. This is where you communicate and storytelling skills and become incredibly important. And then models are deployed into production systems to automate decision making or support ongoing analysis. Now let's go into deep. Step 1, detail defining research goals and project charter. What is the business problem? What decision will be improved? What does success look like? And then you create a project charter, a formal document that clients and stakeholders can agree to upfront. It typically includes a clear research goal, the project mission and the context, how you are going to perform your analysis, what resources you expect to use, proof that it's an achievable project, deliverables, and a measure of success and a timeline. This is not just formality, it is the contract that keeps the project on track. In industry, projects that skips this step often go over budget, miss deadlines, or deliver something the client that actually didn't want. Coming to step 2, retrieving data. This is the project charter. A project charter is a living document for an improvement team that outlines the presenting problem, the target, and the boundaries of a process improvement effort. This slide tells us about the creating of a project charter. A project charter requires teamwork, and your input covers at least the following: the clear research goal, the project mission and context, how you're going to perform your analysis, what resources you expect to use, proof that it's an achievable project or proof of concepts, deliverables, and a measure of success, a timeline. Coming to step 2, retrieving data. Step 2 is all about retrieving data, or as the slide metaphorically calls it, diamond in the rough. Here's the first principle: start with data stored within the company. Most companies have systems for maintaining key data. This data can be stored in databases, data marts, data warehouses, and data lakes. Let me clarify these quickly. A database is primarily for data storage. A data warehouse is designed for reading and analyzing data. A data mart is a subset of the data warehouse geared towards a specific business unit. A data lake contains data in its natural or raw format, structured and unstructured mixed together. But here's the challenge: as companies grow, data becomes scattered everywhere. Knowledge about where data lives often disappears as people change positions. Getting access to data can also be difficult due to privacy policies and security regulations. And if data isn't available inside the organization, you look outside. There are public data sets, third party data providers, APIs, and open government data portals that can supplement your analysis. As I have mentioned earlier, start with data stored within the company. And then don't afraid to shop around. If data isn't available inside your organization, look outside your organization's walls. And step 3, data preparation. Data preparation, also known as data wrangling or data pre-processing. This is the essential process of cleaning, transforming, and organizing raw, messy data into a high quality, usable format for analysis and machine learning. Why is this crucial? Because the quality of your model is entirely dependent on the quality of your data. Garbage in, garbage out. That's a principle you'll hear often in data science. Data preparation includes handling missing values, removing duplicates, standardizing formats, and dealing with inconsistencies. Let me give you a few examples. This is the graph that shows the encircled part influences the model heavily and is worth investigating because it can point to a region where you don't have enough data or might indicate an error in the data, but it can also can be valid data point. These are the graphs that show expected distribution with outliers. These are the distribution plots that are helpful in detecting outliers and helping us understanding the variables. And this table shows the overview of common errors. The general solution is try to fix the problem early in the data acquisition chain or else fix it in the program. And this table shows the detecting outliers on simple variables with a frequency table. Now, coming to data cleaning specific issues, these slides cover some very practical data cleaning scenarios that you will encounter constantly in real world data science work. For example, leading and trailing spaces. When data is imported from different systems, names or codes might have hidden spaces. In Python, you use the strip function to remove these. As it is mentioned here, for instance, in Python, we can use this strip function to remove leading and trailing spaces. But this sounds trivial, but it can cause huge problems. Apple with space is treated as different from apple without any space by computer. The second one is capital letter mismatches are another common use issues. Brazil, as we can see, Brazil starting with capital B and Brazil starting with small b are the same country, but a computer sees them differently. The solution for this is to apply a function like dot lower in Python to convert everything to lowercase before comparison. And the other common issue is impossible values and sanity checks. Sometimes data has value that are physically impossible. Someone with an age of 299 years or a height of 5 meters, these are clearly errors. You write sanity checks, for example, check that age is between 0 and 120. If not, flag that record for review or removal. These small but critical steps ensure your data is reliable before you feed it into any model. This table shows an overview of techniques to handle missing data. Another important part of data preparation is combining data from multiple sources. In real projects, your complete data set is rarely in one place. You might need to join tables from different databases, merge spreadsheets from different departments, or integrate external data with internal records. For example, in our bicycle rental project, we need to combine the rental records internal with weather data external API to build a meaningful data set. This is called data integration and it requires careful attention to matching keys, aligning time periods, and resolving conflicts between resources. As this table shows the joining two tables on the item and region keys. And this table shows the appending data from tables is a common operation but requires an equal structure in the tables being appended. Step 4, exploratory data analysis. This is arguably one of the most intellectually engaging steps in the entire process. EDA is about getting intimately familiar with your data before you start building models. You're looking for distribution of each variable. Is it normally distributed, skewed, or are there outliers? Relationships between variables. Does temperature correlate with bicycle rentals? Missing value patterns are missing value random or systematic. Potential data quality issues that cleaning might have missed. The tools of EDA include scatter plots, histograms, correlation matrices, box plots, pair plots, and more. Libraries like Matplotlib, Seaborn, and Plotly in Python make this very accessible. A key output of EDA is an intuitive understanding that guides your future engineering, a model selection decision in the next steps. These are some of the plots together that can help us to understand the structure of our data over multiple variables. These are some of the box plots and histograms. Now, coming to step 5, building the models. This is the step most people think of when they hear data science, the machine learning part. There are three sub-steps. First one is selection of modeling technique and variables to enter in the model. The second one is execution of the model. And the third one is diagnosis and model comparison. In the first sub-step, selection of a modeling technique and variables to enter in the model, execution of the model, training it in our data. In the second step, execution of the model, it trains our data. In the third step, diagnosis and model comparison, it involves testing multiple models and comparing their performance. And remember, you rarely get it right on the first try. Building models is an iterative process. You try something, evaluate it, adjust your approach, and try again. Let's look at the core predictive models you'll encounter. Regression. Linear regression for predicting house prices or sales. Logistic regression for predicting customer churn or loan defaults. Despite the name, logistic regression is a classification algorithm. It predicts probabilities. Classification. Decision trees and random forests for tasks like predicting Titanic survival or classifying emails. Support vector machines for image classification tasks. Clustering. K means clustering for customer segmentation or market basket analysis. Clustering is unsupervised. There are no labels, and the algorithm finds natural grouping in the data. Deep learning, neural networks for image recognition, speech emotion analysis, fraud detection. These are powerful but require large data sets and significant. Each of these model families has strengths and weaknesses. Choosing the right model for the right problem is critical skill in data science. This is a holdout sample helps us to compare models and ensures that you can generalize results to data that models has not yet seen. Coming to step 6, presenting findings and building applications. This is where your soft skills become absolutely crucial. You might have built the most sophisticated model in the world, but if you can't communicate the results more clearly to a non technical audience, the impact of your work is severely limited. You will present your findings through updated reports, Excel spreadsheets, or PowerPoint presentations. But increasingly, data scientists are expected to build interactive dashboards and web applications that hold stakeholders to explore the results themselves. The lesson here, technical excellence is necessary but not sufficient. Communication and storytelling are equally important skills for a data scientist. Now, I want to introduce you to another important framework, CRISP DM, which stands for Cross Industry Standard Process of Data Mining. Published in 1999, CRISP DM is the most popular framework for executing data science projects. It provides a natural description of the data science lifecycle, what they call the workflow in data focused projects. CRISP DM has 6 phases. First one is business understanding, second is data understanding, third is data preparation, fourth modeling, fifth evaluation, fifth sixth deployment. This business understanding, it involves what does the business need. In the data understanding, it involves what data do we have, what does it look like. In data preparation, it involves getting the data ready for modeling. In modeling, it involves building and training the model. Evaluation, it involves how well does the model perform against business goals. Lastly, deployment involves delivering the model into production. What's special about CRISP-DM? That it's iterative. The phases loop back to each other. After deployment, you might discover new business requirements that send you back to the beginning. This reflects the reality of data science projects in the real world. These slides provide a detailed visual walkthrough of each CRISP DM phase. The framework emphasizes that data science is not linearly general journey, it's a cycle. What I want you to take away is this: whether you follow the O'Neill and Scott process or CRISP DM, the underlying principles are the same. Define, collect, clean, explore, model, evaluate, deploy, and then finally monitor. These steps are universal. This is why we need data science. Due to lack of data available, flights are often delayed or cancelled at last minute. Or due to improper route planning, customers don't get flight for desired time and duration. Or incorrect decisions in selection of right equipment leads to unplanned delays and cancellations. This is why data science is necessary to predict all these. With data science, it has become possible to predict such disruptions and alleviate the loss for both airline and the passenger. Using data science, we can achieve the following: route planning, whether to schedule direct or connecting flights. Predictive analytics model can be built to foresee flight delays, promotional offers depending on customer booking patterns, deciding which class of planes to purchase for better performance. These are some of the examples that why we need data science. So, data science is mainly needed for better decision taking, predictive analysis, and pattern discovery. These are some of the examples that why data science is crucial, and to make decisions clearly, we need data science and data. Data science can answer a lot of other questions as well. Which viewers like the same kind of TV shows? Will this refrigerator fail in the next 3 years? Who will win in the elections? Which route should my cab take so that I reach faster? To answer all these, data science is important. So, finally, data science or data driven science is about asking the right questions and exploring the data, modeling the data using various algorithms, finally, communicating and visualizing the results. This figure shows the data science project process from business objective to data requirement, from data requirement to data collection to exploratory data analysis, from exploratory data analysis to monitoring, monitoring to evaluation, evaluation to deployment, deployment to finally monitoring. Now, let's shift to an important related concept: business intelligence or BI. Business intelligence focuses on analyzing historical and current data to support decision making through reports, dashboards, and visualization. The central question that BI answers is what happened and what is happening now. Key characteristics of BI: it uses descriptive and diagnostic analysis. It primarily works with structured data organized in databases, ERP systems, CRM systems. It focuses on business performance. How is the organization doing? It's used primarily by managers and executives who need to make operational decisions. The typical BI workflow is data sources to ETL, extract, transform, load, to data warehouse, to reports or dashboards, to decisions. Let's look at the common BI tools that are used in industry today. Power BI by Microsoft, Tableau, ClickView, SAP BI, Excel, Advanced Analytics. These are the example cases of BI: sales performance dashboards, monthly review, revenue analysis, inventory and supply chain monitoring, student attendance and performances analysis relevant to your academic domain. Now, let's put BI side by side with data science for comparison. Data science applies statistics, machine learning, and AI to extract insights and predict future outcomes from structured and unstructured data. The questions that Data science answers are more forward looking. Why did it happen? What will happen? And what should we do? Key characteristics of data science are it uses predictive and prescriptive analysis, structured and unstructured data, including text, images, and sensor data. It is model driven. The core outputs are machine learning models. It is used by data scientists and researchers. The data science workflow is data collection to cleaning to engineering to modeling to evaluation and to deployment. The common tools and technologies in data science include Python and R, Pandas and NumPy, scikit-learn, TensorFlow and PyTorch, SQL and NoSQL, and finally Jupyter Notebook. Real world use cases include sales forecasting, fraud detection, crop yield prediction, medical image analysis, and robotic perception models. Now let's compare BI and data science directly using the comparison table. This is very important to understand clearly. Focus. BI focuses on the past and present. Data science focuses on the future and optimization. Analysis type. BI uses descriptive and diagnostic analysis, whereas data science uses predictive and prescriptive analysis. Data type. BI uses primarily with structured data, whereas data science works with both structured and unstructured data. Techniques. BI uses SQL and OLAP, online analytical processing, and visualization. Data science uses ML, AI, and advanced statistics. Output. BI produces dashboards and reports, whereas data science produces models and predictions. Users. BI is used by managers and executives, whereas data science is used by data scientists and engineers. Complexity. BI is of moderate complexity, whereas data science is of high complexity. The key message: BI tells you what happened, data science tells you what will happen next. BI and data science are not competitors, they are complementary. They work best when used together. Here's an integrated example in the education domain. BI provides a dashboard showing student attendance trends over the past semester. Data science builds a model predicting which students are at the risk of dropout based on those attendance patterns and other factors. In the agriculture domain, BI produces an orchard yield report showing how many cashews were harvested last season. Data science builds a model for cashew fruit ripeness detection and yield prediction for the next season. See how they complement each other. BI gives you rear view mirror, data science gives you the windshield, helping you look ahead. Here are some practical project examples across both domains. BI project includes college performance analytics dashboard, hospital management BI system, and sales and inventory BI system. Whereas data science project includes crop disease prediction using DL and student performance prediction and flood risk prediction aligns with your robotics and AI interests. Notice how each project solves a real problem in real domain. This is the mindset I want you to develop. Always connect your technical skills to a real world impact. These are the prerequisites for data science. The following are the three essential traits for a scientist. First is curiosity. Only when you have the curiosity to ask questions, you will have better understanding of the business problem. And then common sense to identify new ways how to solve a business problem and to detect the priority problems. And then last is communication skills. And the prerequisites for data science is machine learning. Machine learning is the backbone of data science. It is one of the many ways the data science uses to find solution to a problem. The second one is mathematical modeling. Mathematical models can be extremely helpful to make fast calculations and predictions from what you know of your data. And the third one is statistics. Statistics is foundational to data science to extract knowledge and obtain better results from the data. And the fourth one is computer programming. You should know at least one programming language, preferably Python or R, for data modeling. And the fifth one is databases. The discipline of querying databases teaches you to ask better questions as a data scientist. Tools or skills that are used in data science. For data warehousing, the skills that required are ETL, SQL, Hadoop, Apache Spark. Tools that required are Informatica or Talend, AWS Redshift. For data visualization, the skills required are R, Python libraries. Tools required are Jupyter, Tableau, Cognos, RA. For machine learning, the skills required are algebra, ML algorithms, statistics, and the tools required are Spark, MLib, Mahout, Azure ML Studio. And lastly, for data analysis, the skills required are R, Python, statistics, and the tools required are SAS, Jupyter, RStudio, MATLAB, Excel, RapidMiner. And the prerequisites for a data scientist and tools and skills required are: a data scientist requires a combination of mathematical foundation, programming skills, data handling tools, machine learning knowledge, and domain understanding. And these are some of the tools or skills that a data scientist should have. Now, let's talk about the people at the center of all this. Who exactly is a data scientist? I love this quote from The Economist. A data scientist is someone who integrates the skills of software programmer, statistician, and storyteller slash artist to extract the nuggets of gold hidden under mountains of data. More formally, a data scientist is a professional who uses mathematics, statistics, programming, and domain knowledge to extract meaningful insights from large and complex data sets. They apply techniques from machine learning, data mining, and predictive analytics to help organizations make data driven decisions. What does a data scientist do? Here are the key roles: collecting, cleaning, and pre processing data. This is the foundational work that takes up a significant portion of time. Building statistical and machine learning models, the analytic core of the role. Visualizing and machine learning models, the analytical core of the role. Visualizing and interpreting data insights, turning numbers into stories, communicating findings to stakeholders, a critical skill that is often underestimated, assisting in strategic decision making using data, being a business partner, not just a technical resource. Notice that these roles span both technical and non technical domains. Being a great data scientist means being versatile. Now, coming to data visualization. These slides extend our discussion of business intelligence and introduce the concept of data visualization, a critical skill for both BI professionals and data scientists. Data visualization translates complex data sets into visual formats that are easier for the human brain to comprehend. Humans are visually weird. We process visual information 60,000 times faster than text. Visual tools include charts, bar charts, line charts, pie charts, the workhouses of business reporting, graphs, scatter plots, histograms, essential for exploring data distributions and relationships, maps, geographic maps and heat maps, invaluable for location based analysis, dashboards, interactive platforms that combine multiple visualizations into a single view. These are the model planning use cases: train data versus test data. Train data is used to develop model, test data is to validate model. Various tools used in model planning are MATLAB, Python, SAS. And these are some of the examples for model building. On analyzing the data, we observe that the output is progressing linearly. Hence, we are using linear regression algorithm for model building in this case. Using test dataset, the build model is validated for the best accuracy. Collected and analyzed data to model building to prediction to output. And this is the another example. Using simple regression algorithm, we have implemented a successful model and predicted the price of 1.35 carat diamond to be rupees 10,000. Now, coming to data scientist. As I have mentioned earlier, a data scientist is a professional who uses mathematics, statistics, programming, and domain language to extract meaningful insights from large and complex data sets. They apply techniques from machine learning, data mining, and predictive analytics to help organizations make data driven decisions. A data scientist need all three. Missing any of them makes you something else. What are all three? There are three sectors: substantive expertise, hacking skills, math, and statistic knowledge. This substantive expertise involves domain knowledge in a specific field, and the hacking skills include programming and engineering ability. Math and statistic knowledge include the quantitative backbone. And there are key roles of a data scientist: collecting, cleaning, and pre processing data, building statistical and machine learning models, visualizing and interpreting data insights, communicating finding insights to stakeholders, assisting in strategic decision making using data. These are some of the responsibilities of a data scientist: management, analytics, strategy or design, collaboration, knowledge. Now, one of the most frequently asked questions is, what is the difference between a data scientist, a data analyst, and a data engineer? These are three distinct roles, even though they are often confused. A data scientist focuses on the future display of data, a data analyst focuses on optimization of the present, a data engineer is focused on building and optimizing the data infrastructure. Think of this way: data engineers build the roads, data analysts drives on those roads to reach existing destinations. Data scientists chart new destinations, they explore where no one has gone before. These are some of the tools that are used for data science like Jupyter, Python, Matplotlib, etc.